In evaluating double integrals, we've done them in Cartesian coordinates and we've done them in polar coordinates. In evaluating triple integrals, we've used Cartesian coordinates and we've used cylindrical coordinates, which are a combination of Z and polar coordinates. There's a third coordinate system that turns out to be useful in some problems, particularly for us when we're doing triple integrals, but they're useful in other situations as well. They're called spherical coordinates. So visualize that we've got x, y, z space. Those are the Cartesian coordinates of a point. We're going to define three coordinates called their spherical coordinates. R is one of them, and it's the distance from the origin to the point. The other two are angles. We drop a perpendicular from that point down to the xy plane. And we talk about that angle in there, theta. And then we talk about the angle from the z-axis down to this line that joins the origin to x, y, z. We call that phi. So we've got these new coordinates r, phi, and theta. We should warn you that in some textbooks, they call this one the phi, and they call that one the theta. I prefer not to do that, because this theta is what we saw in cylindrical coordinates, and I don't want to change his name for spherical coordinates. So that's why I've chosen this particular nomenclature for theta and phi. What we need to know is how to relate the Cartesian coordinates to these spherical coordinates. Well, if you look at this, right, you drop that perpendicular down, then this is a right angle triangle, right? And I ask you then, how long is that? Well, if that's a right angle triangle, right, and this is the r, is not z equal to r cosine of that angle, phi? You could think of, instead of having this, drop a line over there. Draw a line from here, perpendicular to the z-axis, and it would fall right on this one. Then look at that triangle, and this one over that one is the cosine of that angle, phi, all right? All right, the other two. This one, if that one is r cos phi, then this one is going to be r sine phi, that line. Then if you go into this triangle, then this one over that one is the cosine of that angle. So x is going to be equal to then r cosine phi cos theta. And the y is equal to r sine phi sine theta. So these are the equations that will get you Cartesian coordinates if you know the spherical coordinates. But quite often you want the reverse. You want to know what r and phi and theta are in terms of x and y and z, so you can switch from Cartesian over to spherical. Well, certainly I think you would see that since r joins the origin of this guy, r would be equal to the square root of x squared plus y squared plus z squared. That saves you a reason. Theta. Theta is the same angle that we had in cylindrical coordinates and polar coordinates, so there is no really nice form of theta. We had theta was equal to inverse tan of y over x, which doesn't always work. You might need a pi, and you might need a minus pi, so that was not nice, right? Now what we would like is, for every point in space, there is one and only one set of Cartesian coordinates. I would like there to be only one set of spherical coordinates as well, which means I would put a restriction on theta. And I would put the same restriction that we had before. I would choose minus pi less than theta less than or equal to pi. That's the one I liked for polar coordinates, and therefore for cylindrical coordinates, and I'd like to carry it here. Now phi. Now envisage phi. If you want to make sure that everybody's got an r and a phi and a theta, no question about the r, and the theta is going to go wrap once around. Phi is this angle coming down. How far would phi have to go? Well, take phi equal to 0 here, measured from the z-axis. If I hit the xy plane, phi in the xy plane would be pi by 2. If you hit the negative z-axis, then phi would be minus pi. Would you have to go past? And the answer is no. Since theta wraps all the way around, phi does not have to wrap all the way around. It only has to go from 0 to pi. So we would note that. Formula for phi. Well, if I look at this equation, I could say that the cosine of phi is equal to z over r. And then I'd be tempted to write phi is equal to the inverse cosine of z over r. But what I would have to be careful about is the principal values of the inverse cosine function. And the question is, where are they? Well, if you look them up, the principal values of the inverse cosine function are between 0 and pi, precisely what I want. So this then would be a formula that would get you the phi in that range. This is the formula that would get you the theta, as long as you fix up the plus or minus pi if necessary, and this is the formula that would get you the r. All right. Now I did that because I wanted every point in space to have one set of spherical coordinates. Would that happen? And the answer is no, not quite. The origin. What are spherical coordinates for the origin? Answer, r is 0, and theta and phi can mean anything they want. Same thing with the z-axis. Along the z-axis, right, take that point there, then what's r? That's that. What's phi? 0. What's theta? Anything it wants. So points on the z-axis don't have this property that there's one and only one set of spherical coordinates. Does that bother me? Not in this course. If I were doing an advanced mathematics course where I'm doing general transformations between coordinate systems, that would be a problem of concern. But it's not going to bother us. All right, so now that we know what they are, the question is, are surfaces better off in spherical coordinates than in Cartesian coordinates? So let's take the equations of surfaces that we've seen quite commonly and ask, what are their equations in spherical coordinates to see if they're any better? So here's one. X squared plus y squared plus z squared is equal to a squared. You all know that that's the equation of a sphere centered at the origin. What is it in spherical coordinates? Well, x squared plus y squared is equal to r squared. So you got r squared is equal to a squared, and therefore r is equal to a. Well, isn't that pretty? Everybody on a sphere has got a spherical coordinate r equal to whatever the radius of the sphere is. You can see then, perhaps, why these things are called spherical coordinates. They're built for spheres. When you see problems with spheres in it, you immediately think, maybe spherical. Let's talk about some other ones. What about z is equal to 3 times the square root of x squared plus, let's not go that quite yet. Let's go x squared plus y squared. That's a bowl. Seen it often enough. A bowl, right? A circular bowl. Notice, if you plug in there, to switch this into spherical coordinates, I would put z is equal to r cosine phi. I would put x. I would square this one and square that one and add. But notice, if you square this and square this, these two are the same. You'd have cos squared plus sine squared, so you would have r squared sine squared phi. All right? Cancel one of the r's. Say, there it is. All right? Do you like that better? I'm not sure I do. right? So it appears spherical coordinates are not really built for bowls. What if I put that square root back again? Z is equal to, let me put a 3 here, x squared plus y squared. Now we put the r cos phi, and we put 3, but now we got the square root, so we have r sine phi. We could cancel the r's. And what do we got now? If I divide, well, I cancel the wrong one, canceling the r's, so the 3 is there. If I divide by cos phi, I get tan phi is equal to 1 over 3. Phi then is equal to the inverse tan of 1/3. That's a number. So in other words, it's saying cones that have equations of this form are quite convenient in spherical coordinates. If, however, you were to put a 2 under here, it would still be a cone, but now it would be an elliptic cone, and this simplification is not going to take place. Spherical coordinates like circular cones around the z-axis. What about this? X plus 2y plus 3z is equal to 4. That's a plane. If you wanted to switch that to sphericals, you put that in for the x, you put that in for the y, you put that in for z, and you got a monstrosity of an equation. So spherical coordinates are not built for planes in general. Right? What if you put in, say, y is equal to 2x? That's a plane. Now what? Y is equal to r sine phi sine theta, and then you've got 2r sine phi cos theta. You cancel the r's, you cancel the sine phi's, and you got what left? Sine theta is equal to 2 cosine theta. You divide and you get tan theta is equal to 2. Theta is equal to the inverse tan of 2. All right? That's y equal to 2x. You're over here, the first octant. And yes, that's correct. I don't need the plus or minus pi. So that's nice. So vertical planes through the origin are nice because of the theta guy. So certain equations are nicer in spherical than Cartesian, but certainly not all of them. So we'll keep, oops, I erased them. I was going to say we'll keep those equations, and I just erased them. So let me put them back as we might want to refer to them. X is equal to r sine phi cos theta. Y was equal to r sine phi sine theta. And z is equal to r cosine phi. All right. What we want to do is talk about evaluating triple iterated intervals using spherical coordinates. Now remember what we did for Cartesian and what we did for cylindrical. We're going to have to do the same thing for spherical. In order to do Cartesian, what we did was divided space volume into little boxes by drawing x equal constant planes, y equal to constant planes, z equal constant planes, and got boxes. In cylindricals, we drew z equal constant planes that were planes. We drew theta equal constant things, which were vertical planes. And we drew r equal constant things, which were cylinders. And that made that little piece of volume in cylindrical coordinates. We're going to have to do the same thing here, but it is much more difficult to see. So let me make an attempt. We're going to draw r equal constant things. Those are spheres. So let me draw 2 spheres, centered at the origin, reasonably close together. So there's two spheres. Then we need to draw theta equal constant things, which are, as we've seen before, vertical planes containing the z-axis. So let me draw two of them. Let's make them a little closer together. There. Right? They will slice through the sphere there, and there, and there, and there. Right? Can you envisage that? Then we have to draw phi equal constant things. What are phi equal constant things? Phi is a measure of angle down from the z-axis. You say, I want to look at all points that had the same phi. Would that not be a cone with angle phi in there? So if I want to draw two of them, I'm going to be drawing two cones. Now what you have to envisage is those six surfaces would cut out a little piece of volume in space. And the question is, what does it look like? Well, I'm going to try and draw it over here. I'm going to say it's going to have this, 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 and it's going to go back and back and back and behind. And it's going to have this across the top, and it's going to have this, and it's going to go down and have this and this. So what you envisage is this is from a sphere. That back in the back, that's from a sphere. Now, I kind of got that sideways. Probably would have been better if I tilted it, okay? And I tilted it. This is flat on the side. That's coming from the plane. Back in the back, that's flat on the side. And then we've got two more, which are this one and that one. They're coming from the cone. Can you envisage that? I apologize for my argument. Right? We're going to give this thing some dimensions. We're going to call that's coming on a radial line. I'm going to call that dr. All right? Now let's see what else here. Where is this one coming from? Right? Where's that one coming from? So let me make sure I get these straight. All right, so this, we said that was cone, that was cone. So this is angle between two cones. That I'm going to call d phi. And therefore, what's left is this one here to there. That one, angle d theta. What I want to think about is that when this is very small, then it's almost like a box. And I'm going to calculate its volume by multiplying that length by that length by that length there. Right? I think I got this wrong. I think this one is the phi. This one is the theta, but I got it theta. No. This one's a theta. This one's a phi. So what I have to calculate is that length. Well, that's up to you. But this is not straight. It's part of a length along a curve. And the question, how long is that? The same thing here, that length. This length is going to be r sine phi d phi. And this length is going to be r d theta. Both of them are coming from circles. So the ultimate is that dv is going to be all of these multiplied together. So r squared sine phi dr d phi d theta. Now I apologize again because that diagram, it's very difficult to draw that. There's a professional diagram. in the book, all right, that gives you a far better picture of it than this, all right? But the ultimate is that when you go to triple integrals and use spherical coordinates, the dv is going to be replaced by that. Instead of dx dy dz, or r dz dr d theta, you've got r squared sine phi dr d phi d theta. What I want to illustrate is that when we go to a triple iterated integral to evaluate, I've got to interpret what these integrations mean. And I'm going to make a strong recommendation, just like I did for cylindricals. I said, unless you've got a reason to do otherwise, go Z first in cylindrical. I will make a recommendation for spherical, up to you whether you want to adopt it. So I'm going to illustrate by finding the volume of a sphere. We all know what that formula is. Let's see if we can produce it by using a triple iterated integral in spherical coordinates. So let me draw a sphere centered at the origin. Here's the first octant part of it. Let me call the radius A. Don't want to use R, because that would be confusing with this one. I don't want to use little r, because you might think I'm talking about cylindrical coordinates. So I'll use A. So we're going to divide this volume up into these little guys in spherical coordinates. That is supposed to be one of these guys. His volume is r squared sine phi d, d, and d. Yet to be decided what order of integration I'm going to use. I recommend this order of integration, r, phi, and theta. That's always my first choice for order of integration in spherical coordinates, unless I've got a good reason to do otherwise. So let's interpret this. So your first integration with respect to r adds over all of these, I shouldn't say rectangles, these little, whatever you want to call them, right? Radially. You're holding phi constant, that angle's constant, you're holding the theta constant, and you're integrating over all of these things, to me, something that looks like this. Holding the phi angle constant, holding the theta angle constant, and simply adding radially. All right? I'm going to suggest, I'm going to call that a spike. That the first integration adds over all of these little volumes inside a spike. The lower limit then is going to tell me where all of the spikes that fill this volume start. Answer, 0. They all start at the origin. Well, by the way, I am going to look only at the first octant and multiply it by 8 for total volume of a sphere. So what that has produced is the volume in that spike. If I were doing volume and there's an integrand in here, then I would not be producing the volume of the spike. I produce something else, depending upon what that integrand represented geometrically or physically. But here, I'm concentrating on volume. That then, well, I haven't fixed upper limit yet. Upper limit tells me where all the spikes that fill this volume stop. Answer, they stop on the sphere where R is equal to A. That then is the volume of spike. I'm now suggesting that we integrate with respect to phi next, which means you're going to hold the theta constant. But notice, important, in Cartesian coordinates, once we've finished that first integration, the second and the third integration, we interpreted as in a plane. When I did cylindrical coordinates, I said the same thing happens if you integrate with respect to z first, because then it would be an r theta. That's xy plane. It doesn't happen here. There's no such thing as a phi theta plane. And I don't care what order you integrate, there's no such plane after the first integration. You're stuck in space the whole way. So phi. When we integrate respect to phi, we're going to hold the theta constant. Phi is coming down, like this. So to me, I'm integrating over something that looks like that. It's holding the theta constant, it's holding the d theta constants, it's therefore adding over all these spikes that stand in that, I'll call it a slice. So that's what this phi integration is doing. Adding over all of these spikes, standing in the slice, therefore giving me here the volume of the slice. All I have to do is put on limits. Where do all the slices that fill this volume start? On the z-axis when phi is 0. Where do they all stop? On the xy plane where phi is equal to pi over 2. Last integration with respect to theta, then adds over all of these slices, starting here, theta equals 0, ending here, pi by 2. So all you have to do is evaluate that triple iterated interval, and you will get the volume of sphere, 4/3 pi a cubed. And I'll leave you to finish it. Okay? So there's one example. Obviously, spherical coordinates should fit now, because it's got a sphere. Well, here's another one. I'm going to ask for the following. Find the moment of inertia of a solid, say perhaps the solid, of constant density rho. About the z-axis, bounded by z is equal to square root x squared plus y squared, and z is equal to h a constant. So find the moment of inertia of that solid bounded by these surfaces about the z-axis, constant density rho. Drawing it. I'm going to solve this problem, or at least I'm going to set it up in cylindrical coordinates. Then I'm actually going to do it in spherical coordinates. So we've got a cone here, and it's got height h. So there it is. Now, when we defined spherical coordinates, cones were there, right? So when I see this, I might think of spherical coordinates. The plane, however, z equal h up here, which is the top of the cone, does bother me. Spherical coordinates are not built for that. So I'm going to see what happens if I try. But first of all, let's set it up in cylindrical coordinates, and then I'll actually leave you to do it, and I'll set it up in sphericals and do it. So if we do cylindricals, we would say, all right, little piece of volume in cylindrical coordinates, there he is. We want his mass, which is rho d d, d, and we need an r in here. So dz and dr and d theta in whatever order we pick. We need, that's his mass, we need his moment of inertia around the z-axis. But we saw that was the square is x squared plus y squared. That's the square of the distance from this little piece of mass at x and y and z to the z-axis squared. Now we're going to add it. If we integrate with respect to z first, and I would, then we're making columns in the z direction. So columns in the z direction, they go up there and they come down and they hit. Where do they all start? On the cone. I need the cone in cylinder. That's z equal r. That's nice. So z is equal to r. They all start on r, and where do they all stop? They stop on this plane where z is equal to h. So there is, what's that? On the board now is the moment of inertia of any such column around the z-axis. Now I'm going to add over them all, which means I need to take and find the area in which they all project. That means coming down like this, saying it's the projection of that circle. What's the radius of that circle? Well, if you put these together, that's the curve of intersection, which means the square root of x squared plus y squared is equal to h, or x squared plus y squared is equal to h squared. So this is h and this is h. So if we're now projecting down, we get little pieces of very important coordinates. They're already there. And now we add, we go in the r direction, we add over wedges. So r first, theta second. Where does r start? Where do all the wedges start? At the origin. Where do they all stop? They stop when they hit the circle where r is equal to h. And then we add over them all. Right? Now we're doing a little bit of inertia. I've only drawn the first octet here. The parts around the back would have the same moment of inertia. So let's throw a 4 factor in here and then say limits 0 to pi by 2. There. There's what I would have to evaluate if I decided that I'm going to use cylindrical, but in cylindrical, I would replace this with r squared. And that's not bad at all. So cylindricals work out very well for this. Cylindricals like horizontal planes because z is equal to a constant. They don't mind cones, right? This is definitely similar to that. So cylindricals are fine for that. Now let's change. Let's now decide that we're going to do it instead in spherical. So if we do it in spherical, we have these teensy-weensy little volumes in spherical. Right. And we'll add. All right. So we need his moment of inertia, which again is x squared plus y squared, which is and a roll, and the little piece of volume, r squared, sine phi, dr, d phi, and d theta. I am going to choose that order of integration. So there's the moment of inertia of that teensy little volume in spherical coordinates around the z-axis. Now I'm going to add. So I start adding. So what I'm doing is spikes. Right. Lower limit tells me where do all the spikes that fill this volume start? Answer origin, where r is 0. Where do they all stop? They stop when they hit that plane. And I said, that's what I was afraid of when it came to sphericals. The equation of the plane is z is equal to h. But what is z? That was r cosine phi. So on the plane, r is equal to h secant phi. So up here then, h secant phi. That then is the moment of inertia of this spike around the z-axis. Now I'm going to add over them all. So next, phi. Remember, phi comes down, right? Phi comes down. So it will now be adding over the spikes sitting in this slice. Phi limits. Phi starts at 0. All these slices start on the z-axis where phi is 0. Where do they all stop? They all stop when they hit the cone. The cone. The cone. All right, so I've got to take this equation, that's the cone, and I got to transform that into sphericals. Well, z is equal to r cosine phi. And remember, x squared plus y squared turned out to be r squared sine squared phi. There was the x squared, and there was a co-squared theta and the sine squared theta. We saw that before. That was fun. So what have we got here? We've got r sine phi. Cancel the r's, and we've got tan phi is equal to 1. Therefore, phi is equal to pi over 4. That's real. Yes, okay. The angle in this cone is pi by 4. I could have seen that, but this confirms it. So all the slices stop when phi is equal to pi by 4. Now we have to add over all the slices in this first octant, 0 to pi by 2. There. There then is it in spherical coordinates, except I have to replace the x squared plus y squared, but we just saw here that that is equal to r squared sine squared phi. So there it is, totally set up in spherical coordinates. Let's go work on it. This is very easy to do. This is going to create real problems, but it is doable. But I'd like to at least see it happening. So we've got I equal and the 4. Integral 0 to pi by 2. Integral 0 to pi by 4. And we're integrating with respect to r. Let's write here that we've got r to the 4, those ones and those ones, and sine cubed phi. So we're integrating with respect to r, holding the phi's constant. That will be then, and r to the 5th over 5 sine cubed phi. Left to come d phi and d theta. We substitute. Oh, I forgot my rho. I forgot. Oh, no, it is there. All right, so let's pull up that rho. Okay? All right. Substituting now, we got integral 0 to pi by 2, integral 0 to pi by 4. Pull out the 5. So 4 rho over 5. So that's out. Right? Oh, I forgot to put the limits on here. The limits are 0 and, what is it? H sec phi. H sec phi. So we've got to put that in. So we'll have h to the 5th. The 5 is out. Sec to the 5th phi. Sine cubed phi. So that's in there. Put in 0 and you get 0. D phi, d theta. So there's what we're going to have to integrate now with respect to phi. Now the real fun begins. Let's pull out the h. 4 rho h to the 5th over 5. Integral 0 to pi by 2. Integral 0 to pi by 4. And how we're going to integrate. So that one's out. How are we going to integrate sec to the fifth sine cube. I would suggest instead of writing this, that we put under the bottom cos to the fifth phi. How do I integrate that? Think back about the combinations of sines and cosines you need in first year for integration. Any power cos, one sine left over. Any power sine, one cos left over. I can get the former. Suppose I say I'll leave one of the sines and I'll replace the other two with 1 minus cos squared. And then I've got the cos to the fifth at the bottom. D phi and d theta. So what do we got? 4 rho h to the fifth over 5, 0 to pi by 2, 0 to pi by 4. And I'm going to rewrite this as sine phi over cos to the fifth minus sine phi over cos cubed d phi d theta. And what have I got? A power of cos, one sine left over. A power of cos, one sine left over. Those are mentally integrable. So let me do those integrals. Equal them. 4 rho h to the fifth over 5, 0 to pi by 2. Antiderivative in here. Yet to go in then 0 and pi by 4, and an integration with respect to theta. Antiderivative of this, to me, is going to be cos to the fourth in the bottom. Off to the side. If I differentiate 1 over cos to the fourth, my differentiate prime, it would be minus 4. Bring down the power. Lower the power by 1, becomes a 5 downstairs. Go inside and differentiate and get minus sine 5. So what? It says, the two minuses are going to cancel. I need a quarter. 1 over 4. That will cancel out that 4, and I'll be right. Same thing for the other. Minus 1 over cos squared phi. But I guess I'll need a 2 this time. And if I differentiate that, it's going to give me this. Let me think about it mentally. Bring down the minus. That'll cancel a 2. It'll become a cos cubed. I'll get a minus sine phi. 2. That looks good. All right. So 4 rho h to the fifth over 5. Integral 0 to pi by 2 of 1 over 4. I need the cos to the fourth of pi by 4. The cosine of pi by 4, 1 over root 2. Take it to the fourth, 1/4. Minus 1 over 2 cos squared of that. That's a 1/2. Now plug in 0. Right? Now plug in 0. At the lower limit, minus 1/4 plus 1/2 for this one. Still to be integrated with respect to theta. So what do we got here? 4 rho h to the fifth over 5. We've got this constant. This is a 1. This is a minus 1. This is a quarter. I'm going to pull that out here. All right? What's left? What's left is to do the integration. The integration from 0 to pi by 2 of d theta. And that's going to give me, then cancel the 4's. Rho h to the fifth over 5. Integrate pi over 2. Integrate, get 1 and plug it in. So there's the answer. Rho h to the fifth pi over 10. Rho h to the fifth pi over 10. Now that is what I would call a non-trivial integration in doing but it worked. But the reason it was not pretty, again, was because spherical coordinates don't like z equal constant planes. That's where all the problem came from, was that this was the equation of the plane kind of thing in spherical coordinates. It didn't like it. Cylindrical said, I do. So do the cylindrical one and see that you get the same answer as that. So there's a couple examples then using spherical coordinates for triple iterated integrals. That finishes the videos in the course.